I'm going to talk about classification of Skew-Hadamard matrices of small orders. This is a joint work with Hanaki, Kharagani, and Mohammadi. So let's start with the definition of Skew-Hadamard matrix. We call a Hadamard matrix H, Skew-Hadamard, if H plus H transpose is equal to two identity. Here is an example. The entries on the diagonal are always 1. And if you take an entry here, for example, this one, the opposite one here is negated. This is 1, and here is -1. So it is a kind of a skew matrix. Skew-Hadamard matrices have some applications. For example, they can be used in constructing doubly regular tournaments. In fact, they are equivalent to doubly regular tournaments. Also, they can be used in constructing orthogonal designs, association schemes, self-dual codes, strongly regular graphs, and some other objects, combinatorial objects. First, I define, because we are going to talk about classification, I want to define equivalence here. We call two Hadamard matrices H1 and H2 H equivalent or Hadamard equivalent if H1 is obtained from H2 by some operations like this. You can permute the rows, you can permute the columns, you can negate some rows, you can negate some columns. In other words, we call to H1 and H2 equivalent if we have this relation. H2 is equal to P H1Q. Here P and Q are signed permutation matrices. This is exactly the meaning of this in the algebraic form. You have Q is a signed permutation matrix. It means that you can permute the columns, you can negate columns, and also for rows P. We also need to define Skew-Hadamard equivalence here, SH equivalence. Two Skew-Hadamard matrices H1 and H2 are called SH equivalent if we have this relation. H2 is equal to P transpose or P minus 1, H1P. So the permutation on rows and columns are the same. The permutation we are applying on rows is the same as the permutation we applying the columns. Also, the pattern of negations of rows and columns are the same. So here is a table of the known results on classification. You see the order of the order here up to 36, and the second row shows the number of Hadamard matrices. Here you see, for example, in order 32, we have about 13 millions of equivalence classes. The last two rows is about Skew-Hadamard matrices. The first row shows the number of Skew-Hadamard matrices in H equivalence, and the second one shows in Skew-Hadamard equivalence. As you see, the classification is known up to 28, and we here trying to extend this classification to order 32 and 36. So we want to find these entries here, here, and here. So first we trying to order 32. So the question is that how many Skew-Hadamard matrices exist in order 32? We use the classification of Hadamard matrices in order 2 and order 32. This classification is known. There are about 13 millions of them. We use this classification and try to extract all classes which contain some Skew-Hadamard matrix. For this, we use this lemma. This is a lemma by Langier from 1976, which says that Hadamard matrix H is equivalent to a Skew-Hadamard matrix if and only if there is a sign permutation matrix P such that H times P is a Skew-Hadamard matrix. So instead of multiplying H from left and right by sign permutation matrices and then to see if it is skew or not, we just need to consider multiplication by right or left. Here we consider by right. It's the same, right or left. So also we can find the pattern of signs in this sign permutation matrix by just looking at the diagonal by observing that the diagonal entries of HP must be 1. This is the definition of a Skew-Hadamard matrix. The entries on the diagonal must be 1. So here is a classification process. Let R show the set of representatives of all these classes in order 2, in order 32, and take a class that H belongs to R. We try to find the sign permutation matrix P such that HP is a Skew-Hadamard. For this, we construct this matrix, this sign permutation matrix, column by column. To construct column I, so at step I, we construct column I of this matrix P. We choose column I. We consider all possible possibilities for column, and for each possibility, we check that the principal submatrix of HP in the first I rows and columns to be skew. Also, the diagonal entries must be 1. If not, we backtrack. If it is okay, we proceed forward. If not, we backtrack and we backtrack to step I-1. So in this way, we construct P. If we find a P, then we obtain that class contains a Skew-Hadamard matrix. The procedure stops if P is constructed, which means all columns of P are chosen, or no P was found, which means that that class doesn't contain any Skew-Hadamard matrix. Here an observation to, in fact, to make the procedure possible in terms of computational time. We have all the classes, about 30 millions of Hadamard matrices in order 32. And if we look at these matrices, these representatives, we find that they have symmetry, high symmetry in the first rows and the first columns. This is because of the method of constructions. When we had constructed these matrices a long time ago, say about 10 years ago. The procedure was so that the first rows had high symmetry. This high symmetry prohibits the algorithm from backtracking in earlier steps. It is good to backtrack as early as possible. It saves time for us. To resolve this problem, we applied a random permutation to the rows of every element of R and broke the symmetry. So it helped the algorithm to backtrack earlier, and it made the search computationally possible. Here are the results. There are exactly 66, 62 H equivalence classes and 72, 27 SH equivalence classes of Skew-Hadamard matrix of order 32. So back to the table, we have filled these two sets. Okay. Excuse me 1 minute. Excuse me. Now we are going to classify Hadamard matrices in order, Skew-Hadamard matrices in order 36. Here we don't have a complete classification in order 36 for Hadamard matrices. So we cannot use the procedure we used in 32. We are going to construct Skew-Hadamard matrices directly. So we present an algorithm that constructs Skew-Hadamard matrix directly. So to do this, we need to define types. Type is a notion which has been defined long time ago and was used in classification of Hadamard matrices. I think order 28. So take H Hadamard matrix of order n with entries Hij, and we look at any 4 rows, rows I, J, K, L, any 4 distinct rows, and we transform these 4 rows in this form. The first row is completely bound, plus 1, and the second row is looks like this. Half of them are plus, and the first half entries are 1. The last half is -1, and the third one, the fourth row. Any 4 rows can be transformed into this form, and here S plus T is n over 4, and T is between 0 and n over 8. And we define the type of these 4 rows I, J, K, L as T. So the type of this is T. This number is T here. So the type is a number between 0 and n over 8. And the Hadamard matrix is called type B between a number between 0 and n over 8. If it has a set of 4 rows of type B and no set of 4 rows of type less than. So if you look at order 36, here n is 36. 36 over 8 is 4, and the possible types are 0, 1, 2, 3, 4. But we know that type 0 and type 4 are not possible. It's no results. So the only possible types are 1, 2, 3. And here is a lemma we use for in the classification. It's about type 1 Hadamard matrices by Kimura, 1994. It says that if you have a Hadamard matrix of type 1 in order n is 4 modulo 8, then its transpose is also of type 1. If you look at the transpose, it is also type 1. And so when H is a type 1, it means that you have 4 rows in this matrix, which are of type 1. And the lemma says that there are 4 rows in the transpose, which are of type 1. And the point is that we know which rows are exactly type 1 in transpose. We can find those 4 rows which are of type 1. To classification, we need to look at the 4 by 4 skew matrices. This is the 4 by 4 skew matrices placed in the upper left corner of Hadamard matrices. There are two possible matrices for up to equivalence A and B. So if you look at the first the 4 rows of type 1, we look at the first 4 columns. Here it is of type A. It's matrix A here and here, and we have transformed in this form, which can be seen. It is of type 1. And if we look at these 4 columns, column 1, column 3, and this column shown in red, these 4 columns are of type 1. So the transpose is also of type 1. The second one can be transformed to first one. It is easy by just permuting rows and columns. So we just need to consider the first one in the classification. For matrix B, here is matrix B in the first 4 columns. Matrix B here. There are 2 possibilities for the other columns. Here you can see. The first example cannot be possible in a Hadamard matrix, in a Skew-Hadamard matrix, because if we look at the first 4 columns, it will be of type 0. And we know that in order 36, we don't have type 0. So we remove this one, and we just focus on the second one. And here also, if you look at the red columns, they are of type 1 in transpose matrix. Again, we back to matrix A. We have these 4 rows, and we are trying to complete this partial Hadamard matrix to a Skew-Hadamard matrix, to a full Skew-Hadamard matrix. We search for possible solutions for row 5 and row 6, and it is found that rows 5 and 6 are unique. It is because of the nice structures of these 4 rows. Then we go to the next rows, rows 7, 8, 9. We find 9 solutions for 7th row. Also, so many for row 8 and row 9. And these solutions are up to equivalence. We do permutations on rows and columns and relations of rows and columns as much as possible to find the solution up to equivalence. And we extend this number of solutions, 3,751 solutions to the full Skew-Hadamard matrix. And in row 36, we find about 200,000 solutions. This is because of equivalence check. And after equivalence check, we find about 23,260 Skew-Hadamard matrix up to equivalence. That was for matrix A. For matrix B, we find that the number of solutions for row 5 is about just 2 solutions. For row 6 is about 146. For row 8, about 1,000 solutions up to equivalence. And then we extend them to order 36. We find about 700,000 solutions. And after the check, after equivalence check, we find about 145,000 solutions. Some of the solutions is considered before in matrix A, so we remove those solutions and we find them this number. Here is the result, the summary of the result. It shows that there are exactly 146,586 type 1 Skew-Hadamard equivalence classes of Skew-Hadamard matrices in order 36. I don't know exactly how many Skew-Hadamard matrices was known before this classification. Maybe, if I remember, less than 100, maybe something like that. Okay. To do an exhaustive search, we try to do that, and we need a definition for classification, and this is the notion of canonical form. We need to define canonical form. This canonical form are exactly those matrices which we generate during the search. So a Skew-Hadamard matrix is called in canonical form if the row vector obtained from tracing the entries. We trace the entries of Hadamard matrix in the following order, and if the row vector is the biggest one among all the equivalent matrices, we call the matrix in canonical form. And the order is just is like this: take the entry in position 1, 2, row 1 and column 2. Then take the entry in row 1 and column 3, row 1 and column 3, row 2 column 3, and row 1 column 4, and etc. So in this way, we trace the entries, we make a big row vector, and if it is the biggest among all equivalent matrices, we just call that one in canonical. And these matrices are just what we are looking for. And here is the procedure to do that. First, we find the solutions for 14 by 14 submatrices placed in the upper left corner of a canonical Skew-Hadamard matrix of order 36. For each one of these, for each one of these solution, we extend it to a partial Hadamard matrix of order 14 by 36. So we complete rows, the first 14 rows, using an exhaustive search. And then for each partial Hadamard matrix, which is of order 14 by 36, we complete every row by solving a system of linear equations. If we do the procedure, let me show you how many solutions are for 14 by 14 submatrices. There are about 80 millions of them. So for the upper left corner, we have about 18 possibilities for matrices in canonical form. We have a completed search for about 10 millions of them. And if we look at these 80 millions of them, and if we sort them by alphabetic order, we have tried some from the first ones and some from the last ones. Totally about 10 millions of them, and so we couldn't complete the search, the exhaustive search. We just did the search for so many of them. It took a lot of time to do search for all these 80 millions. And for these 10 millions of them, we have got these results. We have found that there are at least so many type 1 Skew-Hadamard matrices. And also we have found at least so many Skew-Hadamard matrices of type 2. If you look at this number, 146,586, it is just exactly the same as this number in this theorem, which was the complete classification of type 1. So in this incomplete search, we have found all type 1 Hadamard matrices. And we have found some other matrices which are of type 2. And there's a question, is it the complete list of Skew-Hadamard matrices in orders 36 or not? It is quite possible that this is the complete list, and we may have no more Skew-Hadamard matrix of order 36, which means that there is no Skew-Hadamard matrix of type 3. They are just of type 2, type 1, and type 2. In the final, let me give an application of these results in association schemes. Let me define association scheme. Probably most of you know about that. So I go fast through the definition. And Association scheme of order n and class D is just the set of D plus 1 matrices. The first one is identity. These are n by n matrices. Entries are 0 or 1. And the sum of D matrix, all matrices is just J, the all 1 matrix. And for any two of them, first A sub A transpose, and then A sub A and A sub J are linear combinations of the matrices. And it is well known that each matrix in the here have the same row and column sum. So row sums and column sums are the same. And we call an association scheme symmetric if the matrices are symmetric. If these matrices are symmetric, we call the association scheme symmetric. Here is an association scheme of order 3 and class 2. So the first matrix identity, this is the second and the third matrix. And if you sum up these matrices, you find J, matrix J, the all 1 matrix. And also, if you multiply two of them, you find that it is a linear combination of these 3 matrices. And we just consider association schemes of class 2. So we have matrix A, I, matrix A, and the matrix J minus A minus A. This is suppose that this is the association scheme of class 2. If A is a symmetric, if this matrix is symmetric, then association scheme is symmetric. And it is equivalent to a strongly regular graph. It is just a strongly regular graph. It is nothing more than that. And so we just forget about the symmetric case and let us focus on non-symmetric case. Non-symmetric association schemes of class 2. Here is a correspondence between Skew-Hadamard matrices and non-symmetric association schemes of class 2. It says that if n is an integer multiple 4, and we have a non-symmetric association scheme of order n minus 1, then from this scheme we can find the Skew-Hadamard matrix. The matrix looks like this. The first row is 1, the first row is 1, and the column is minus 1. And here we put I plus A minus J minus A minus A. And it is easy to check that this matrix is a Skew-Hadamard matrix. It's easy to check, just multiply by transpose and see that it is Ni, and so it is a skew. It is clear that it is skew. So this is a correspondence, one-to-one correspondence. If we have a Skew-Hadamard matrix, then we can find a non-symmetric association scheme. Here is an example. We take a Skew-Hadamard matrix of order 4. We have made the fourth row and the fourth column 1. Here, if you look at the fourth row, it is just only 1, and the fourth column minus 1. And we can extract the matrix A from here. just look at this code here. And the first 3 rows and the first columns, the first 3 columns, and take 1 here and 1 here. This is A, and for the second matrix, take -1, -1, -1, keep 1, 1, 1. So we can use this correspondence and our results on order 32, and we can find this theorem. The theorem says that there exists exactly so many isomorphism classes of association schemes of order 31. As we talked before, class 2 is about Skew-Hadamard matrices, the non-symmetric ones, and we find these association schemes from Skew-Hadamard matrices of order 32. From that complete classification, and these numbers, the unique ones, are just found from theory. The theory says that they must be unique. And this is the last slide, and I want to stop here.